Good morning to all of you. Today we have the second session. Please confirm whether you are listening me, whether you can hear me. This is Professor Nijjhot Dhang from IIT Kharagpur, and today I am starting now the design of reinforced concrete structures, that part 2. As we have just yesterday many theories, and all we know that only theory will not help us. We need some kind of problem solving, and that is the objective of an engineer. Coming to that one, before solving the problem, let us come back to the code which we follow. Let me show the code which we follow for reinforced concrete design. This is the code. I have already shown the first page, that plain and reinforced concrete code of practice, and this is fourth revision. Last revision was in 1978, and this one you see that IS 456 2000. So this is, I am not going to detail of all those things page by page, but I'd like to show you the relevant portion of the code which we use it. So as you can see, it is maybe difficult to see, just to give you idea that where that few pages that where I am interested, that I shall show you, because the code you should follow and you should be familiar with that. I am not getting any confirmation from any of you. Please just confirm that whether you are there and you are hearing me properly. Then it will be helpful for me. Okay. Oh, fine. Thank you. Thank you very much. So because as you know, it is difficult that without seeing any students, but anyway, I'm sure that you are listening me and enjoying that this discussion, because first I should introduce today that code, that IS 456. There are so many pages. One thing you just see this particular one here, that EC. আচ্ছা এটা কি একটু বড় করা যায়? So this is EC equal to 5000 root FCK. FCK is the grade of concrete that characterizes strength, that is M20 means 20 Newton per square millimeter, 25 M25 means 25 Newton per square millimeter. Because this one you require EC will be modulus of elasticity in short term, static modulus of elasticity in Newton per millimeter square, that we have to use it for frame analysis. Then only we can get the bending moment shear force. So far we are talking for a particular section. Tomorrow we shall come in detail for a particular frame which already I have circulated. Now coming to this one here, the different parts code, I am not following all those things, because as you know that in the very beginning, at this age, you will not be able to appreciate the importance of code. And it was true for me also when in long back, in 30 years back when I was a student. That time also I was thinking that what is this code? It looks like the code is boring, but later on when you will in practice, this is the code. If you follow, and it will save you. Nobody can question you that why you have taken that one, why you have not taken this one, because if you follow the code, this is the convention. This one will be the Bible of design of concrete structures. So coming to this particular one here, different things are there. I am not telling the, because allow me to go to page by page, because I shall be able to go, then it will be easier for you. So coming to this one, there are so many things are there, inspection and testing of structures, like that, so many things are there. But for design purpose, where we are interested, that we shall consider here. So this is the one section, general design consideration. So thank you very much for your confirmation for that voice and video clear. So coming to this one, I would like to show you that this is table 12 and table 13. Why do we require this one? Because sometimes it happens, it is not possible for us to calculate that, analyze the structures detail. In that case, what we do actually, we consider this one, that certain tables that we follow, and this table actually bending moment coefficients, that is actually table 12, and this is table 13 for shear coefficients. Now one thing I would like to inform you, that dead load and imposed load fixed, and imposed load not fixed. So what does it mean? This portion is called span moments and this one is your say support moments. So if we consider that, then what we can do, just let me draw a figure. So this is a beam, it may be fixed also. So like that it is going. Now what happens here? We have to find out the bending moment and shear force. That is our objective. Then only we can go for design, because first we have to find out the bending and shear force. Where do we like to find out? We would like to find out here in this support. So that means one at this point, another at this point, one here, like that I shall go. So now the thing is that one is we are having self weight, and also we have that imposed load fixed. So another one is we have imposed load not fixed. So what does it mean imposed load fixed? So for this case, near mid span, just to give you that one, that this particular point we are having 1 by 12. Just to give you one example, this is 1 by 10. So 1 by 12 actually less than 1 by 10. 1 by 10 actually more, and 1 by 12. That means here just it may be difficult for you to understand. So 1 by 12, it comes as 0.0833, whereas this one has come as 0.1. So as we can see, 0.0833 is less than 0.1. Now this is fixed and this is not fixed. Superimposed load fixed and not fixed. I do not know whether you are sitting on the bench or you are sitting on the chair. If you are sitting on the chair, possibly those chairs are movable. But if you sit on the bench, and possibly the benches are fixed on the floor, and in that case benches you cannot move it. That means if you sit on the chair and then all of you can actually assemble in one place, and on the basis of that then means in one place of the room that whole load can be actually concentrated, dumped. But if it is say fixed, that means benches, then obviously it is not movable. So obviously that one will have that not fixed condition. That means in that case, that particular one, if it is not fixed condition, that means you are giving that more safety. But if it is say fixed, that means you will not be able to move. This is the idea of that, and we calculate that one. We do for analysis. There are many softwares are available. You can write down your own software also. But the basic thing is that coming to this particular code, please give this. Coming to the code here, this particular one. Hello. No, okay. Oh, this is coming, right? Okay, thank you. So if you see this one here, that 1 by 12, that is near middle of end span at middle of interior span. Why we are telling near middle? This one I can show you by a simple example. Let us consider this beam. The bending moment here like this. So this is your support, but this one will not be in the middle. It is not in the middle. But here this one will be at the middle. So that's why at the we call it the near middle of end span. That is your, we consider that one when we are considering this is your end span, this is your intermediate span, in this case 1. But whereas here we can consider this one intermediate span like that. So you can find out the your say bending moment coefficients from here, and from there you can find out the bending moment. That means this table 12 and 13, these are very useful in absence of your any analysis thing, you can immediately start your calculation based on these coefficients. To find out bending moment, use table 12 and use table 13 for shear force. Now, there is one thing you see, that one at end support, again fixed and not fixed. At end support you are having 0.4 and 0.45. Obviously that when it is not fixed, then it will be more, but if it is fixed, then it is less. Now, why there are two at support next to the end support, outer side, that means this is your outer side, this particular one we call it outer side. And hello, please give me the paper. Oh, paper given. Okay. So this one, if we give this one, so this is one, we call it actually outer side, and this one we shall get it here, that inner side. So that's why we get actually two. Here we shall get shear forces, one this side, another this side. I mean, for each beam, for both ends, we shall get the shear force. So this is the one very useful. You can immediately find out. Now the issue is that how much is the load? Let us consider this is said something W. Maybe say I can say W kilonewton per meter. And let us consider this is length L. So if it is length L, so this bending moment say A and this one say your B. So MB will be equal to 1 by 12 WL square for fixed, and if it is not fixed, then MB equal to 1 by 10 WL square. So this W we can calculate, and we know the L span, so we can find out 1 by 12 WL square 1 by. So this is the bending moment we shall use for our design. So at any section, similarly I can find out here also, I can find out here, I can find out all the points I can find out, and for design purpose you have to check all of them. That means you have to check at this section whether it is all right or not, at this section. So like that you have to check. It's not the only one section. One way you can do it, that if you do not have much time, then what you can do, that you can take a section where you are having the maximum bending moment, and for that you can check and that you can provide, and obviously that one will not be economic. So because first thing, that one the structure should be safe. That means for design purpose, objective of the design, that the structure should be safe, that is the first criteria, and second criteria, that it should be economic. Now yesterday I have shown you regarding that T-beams, other things, so which I have shown you from this particular that page of this code. So like that we are having so many things. Just to give you idea, one more thing. So there is one way that how to find out the value, because the thing is, the problem is given just a single line and it is told that you just find out the section. What will be the depth, initial depth, how much you will consider, that we consider from here. That means for basic values of span to effective depth ratios, for spans up to 10 meter, cantilever then 7, that means a span by depth, that will be 7, simply supported span by depth 20, and continuous span by depth 26. So that means from here, if you know the span, immediately you can calculate what will be the depth of the section. So that means here, if we consider span by depth equal to 20 for simply supported case, so I can find out depth equal to span by 20. So this is the initial guess. Now there are certain more things are there, slowly you will come to know, but for the time being you can consider that one initial guess can be dependent on this clause number 23.2.1 of IS 456, where it says that basic values of span to effective depth ratios for spans up to 10 meter, cantilever 7, simply supported 20, continuous 26. There are many more things are there, because life is not so easy that it will be always less than 10 meter. So, spans above 10 meter, the value in A may be multiplied by 10 by span in meters. So, I have to reduce that value, so that if I can reduce the value, the depth will be more. So, I can give you example. Let us consider this one here, say 15 meter. So, 15 meter span. So, if it is having 15 meter span, so first you are getting depth equal to 15 by 20, this much, and then modify into 10 by 15. So, we can find out this particular one here, that we can find out, and then, but this is true for cantilever beam only. So, we can find out on the basis of that, we can find out. So, sorry, this is the one 15 by 20, that particular one we can consider, and then sorry, this one we can consider as 20, just one sec. So, span by depth equal to 20 into 10 by 15. So, then it becomes 200 by 15, which is coming as 13.33. So, that means here for 15 meter span, depth will be equal to 15 meter, that means 15,000 millimeter by 13.33. So, that means here this 20, that is come less, that means here in this case the value will be more, the depth will be more. So, which is coming as 1125 millimeters, say roughly. So, approximately you can consider that 1125 millimeters. So, as you can understand that we can use this particular code for this clause to find out the initial guess of the depth, because you do not know, because you have not done the bending moment analysis, other things. So, this is the first thing, this is very, very important, that span by depth ratio. Later on you will find out that this one will help you, this one will help you to find out, this one will help you to find out the value that your say deflection criteria also. Just quickly I am going through the code, relevant portion. There are so many things are there, because in the very first one it is not a good idea to go more detail. When you will, after completion of this course, you will find out that there are many more things which you can understand very easily. So, now coming to the one, I am not coming all those things, just quickly I am going through these different pages quickly, because our main objective to show you the limit state method. And whatever we have discussed yesterday, we have taken this curve also from there. As you can understand, we have taken the curve from here, and we find out the strain. For a particular strain, we can find out the stress also. We shall solve one problem, and so that we understand. And there are all the cases are there here. Yesterday we have discussed on the shear stress. So, this is the table 19 which we use. So, for M15, M20, M25, M30, M35 and M40 and above. So, for if it is M45, then we shall use the same one, and we are having different percentage of steel, that means up to 3% we can go. And yesterday also I have shown you that maximum shear stress. So, this is available here, because I thought that I should actually show you that where it is available, because IS 456 where it is available, that should be known to you also, because these are the tables we extensively. So, table 12 we have already discussed, table 13 already we have told, and another table we have told, table 19. Now, one more table we use it, that we shall use it, one more table. So, for design of slab, this is one, that's design of slab, two-way slab. So, this table 26. So, for the time being, table 12, table 13, table 19, table 19 and table 26. So, these are the tables you can use it. There are many more things are there, but introduction it will be more than sufficient, and we shall solve few problems also with that. So, this is one, just I thought that I should show you that where from we are taking. This is the columns, other things that also use it, later on we shall find out. The crack width I have told, regarding your say serviceability limit state, we calculate on the basis of that, but we are not going to detail about all of them. That would now the thing is that only thing I would like to say that yesterday we have shown you that XU by D 0.87 FYAST by 0.36 FCK BD or MU equal to this much or MU equal to this much. So those things actually we use it from Annex G of IS 456. You can do, we have derived it also yesterday, but these are the things which is available here. Similarly, we shall find out that you would say for doubly reinforced section, for plain section, all those things we can find out. So this is the thing I thought that I should actually show you regarding the code which we extensively use it. We shall come back later on with the IS 1893 for your earthquake analysis, but let us come back here now today that with the problem. So design of reinforced concrete structures, let us see that few problems and then it will be clear what we are going to do. So let us consider the problem first, that design a beam to carry a design moment of 200 kilonewton meter using concrete grade M25 and steel grade Fe415. So this is your objective. Now question is that one, where from you have got this 200 kilonewton meter? Who told you that we shall use M25 or steel grade Fe415? So because most of the cases you will find out in the book that it has started with say your exercise or example, some numerical value given, and on the and then also they are giving certain say grade and steel grade, and obviously I am also not in exception, so I am also following the same path. But anyway, this 200 kilonewton meter actually we are getting from our analysis. For the timing, if you are interested, then you can find out from the one that from 12 using 12 table 12 or table 13 also. I can give you just one example here, this particular one here, as if let us consider a simply supported beam and having certain length L, and you are having certain W. So then this W and this is L. So M here, this is M, and this M will be equal to here WL square by 8. So now I would like to find out MU, which will be certain factor multiplied by again WL square by 8, and this one we generally take 1.5. So this is the value, we take it 1.5 here, that means, and this is called design moment. So here we are considering here, and then we have taken M25 and Fe415, that grade of steel. We can use Fe500 also, but mainly we are using M25 and Fe415 we are using. So now let us go step by step, and we are interested here that a particular section, we are interested here to get a particular section, and that section I have to provide the reinforcement. This is called longitudinal reinforcement. So this is your B, this is capital D, and this one we have say small d. So we are interested here, and we have to find out that how many, what is the area of steel and how many bars shall we provide. So let us go step by step. So characteristic strength of concrete FCK 25 Newton per square millimeter, because it is M25, so 25 Newton per square meter. Characteristic strength of reinforcing steel, because I am considering this one, why I prefer always not the steel, I always prefer to use reinforcing steel, because the other one we are having structural steel. That means whenever we will do the design of steel structure, there we will find out that is called structural steel. So this one, to distinguish, I always prefer to write the reinforcing steel, and that is Fy equal to 415 Newton per square millimeter, because this is Fe415. Design moment Mu 200 kilonewton meter. width B 250 millimeter. This one generally guided by the practical point of view. So let us consider that you are using say 250 millimeter thickness wall. So obviously we can use that thickness of the beam, that 250. So this is always guided by that. There are, whenever you are going to design, there are few basic values that is actually you have to assume or you have to provide, and then you have to find out the other thing. That means in this case the depth is dependent on the strength, depth is dependent on the load, that how much bending moment is coming. That's why this is not, you cannot provide just simply whatever you like, you cannot provide. You have to provide that what is coming from the point of view of the applied load or applied moment. In this case 200 kilonewton meter. That means I have to find out a depth of the beam such a way so that concrete also will be able to resist that and steel also will be able to resist that, because this section roughly you can say that you are having this type of thing, that's considering the strain, you are having this. That means this side one compression, this side you are having tension. So coming to this one here, you are having design moment 200 kilonewton meter, width B 250 millimeter, overall depth say let us say I have considered here just 600 millimeter, that I shall check it later on. Clear cover the CC, that is 25 millimeter. What about the coefficient QB? That one I am considering, because that you know all know 0.138 FCKBD square, 0.138 FCK. That value we can calculate with 0.36 into XU by B, that balanced one, which you can get also from the IS code also 0.48 into 1 minus 0.42 into 0.48. This is the value I can get coefficient, that I am getting it here, which we have discussed actually yesterday. We have discussed this particular one here. And this one, moment of resistance due to concrete, that one will be QB into FCKBD square, which is nothing but 0.138 FCKBD square. So 276.851 kilonewton meter. So as you can see, this is the value I am getting it here, that 276, which is greater than 200. That means the one depth we have provided, that is actually your that value we can say that it is safe. I can do it other way also. What I can do? I can do it other way also. I can find out this one here. That means depth D equal to square root of mu by 0.138 FCK B. From here also I can find out. So let me try here then. Just please allow me, so that I can find out and I can tell you how much value you are getting. So I am getting D equal to 481. So I am getting D equal to 481. So how much I require? The D required, that means depth required 481 plus 25 plus say I am using something say 20 dia bar. So what I can do here, that 481 plus 25 plus 10, which is coming as 516. That means if I provide say 525, that is also all right for me. But here I have used say 600 millimeter, and then obviously it is all right. That means in this case also, if you use 525 millimeter, that is also all right. So you can do it other way also. Here I have done what I have done here. I have calculated, I have taken the D 600. Obviously this is from experience, but you prefer, you do in this particular fashion. You go ahead with the value, say you find out the effective depth required, and on the basis of that you calculate how much to be provided. And generally you find out in the book also in that particular manner. So now obviously I can show you this moment of resistance due to concrete. That means concrete also it has to resist that moment of 200 kilonewton meter. Similarly steel also resists. So both of them, because if one of them fails, then the structure will fail. It is some kind of, say, you can consider say link, one link after another. So both links should be safe. If one link fails, obviously that, as if you are having say one chain, and with that you are actually holding that one, that chain. Now let us say that particular chain, that one of the link, if it fails, then it will fail. That means it is some kind of, you can say, series. That means if that is not like that, steel will fail or concrete will fail. If any one of them fails, the structure will fail here. Now the next one, I have to find out what is the value of, how much is the area of steel I have to provide. That is the next question. So here I have found that lever arm factor J, the lever arm, and this particular formula, that one very useful formula, that 0.5 plus root over 0.25 minus mu by 0.87 FCK BD square. From there I can get that one value J equal to 0.868. So this value, that 200, that is the applied moment, I have put it here, 0.87, FCK is 25, B is 250, B I have provided here this particular one, basis of that I can find out D 567, and so I can calculate that 0.868, that value I can find out here. So area of tensile reinforcement required, mu by 0.87 FYJD, mu by 0.87 FYJD, just to give you idea that what exactly it means, that we are having a section, this is the area of steel I have to provide, this is my depth, overall depth, then I have D, this is B, the section looks like this, so this is C, whatever we have discussed yesterday, C and T, and let us use another pen, and this one, that is your Z, which is nothing but JD. So this J I have to calculate, and that J we have calculated based on the equation, that derivation, other things, that J equal to, very simple formula, you just remember this one, 0.5 plus root over 0.25 minus mu by 0.87 FCK BD square, where from there we can find out that value. So coming to this one here, so I can find out this formula and I can use it, that mu equal to T times Z. T is how much? 0.87 FYAST. So T times Z, so I can write down 0.87 FYAST multiplied by Z means JD. That means AST will be equal to mu by 0.87 FY JD. This is the formula we have used. That means this is the couple it is making. So T times Z, and which you are using this particular formula. So you can get this particular formula, I can get it here. So area of tensile reinforcement required 1125.2 millimeter square. Tensile reinforcement bar you have provided 16 millimeter. Number of tensile bars NT equal to 6. Area of tensile reinforcement provided, that means 1200. That means 16 means actually the bar means 201 square millimeter. 6 into 201, this is 1206. So requirement 1125 and you are providing 1206. That means it is all right. Also, I can calculate that as per the clause of that I have already shown you in IS 456. Using that formula, you can find out how much is the moment of resistance. That means if we provide this reinforcement 1206, then I can get 212 kilonewton meter. So what does it mean? It means 212 kilonewton meter. It means that it is greater than 200. That means your applied moment is 200 kilonewton meter, and if you see the concrete, that concrete can resist up to 276 kilonewton meter, and steel can resist 212 kilonewton meter. So what does it mean? The steel will fail fast. That means if you keep on applying load, if it goes beyond 200 kilonewton, so if you go to 212, then first steel will fail, because concrete is having the higher strength of 276. As if you can consider that one is steps in a staircase, you are having one step there, that is the requirement 200 kilonewton meter, but you are providing certain steel at another step, that is a 212 kilometer meter, and you are keeping that concrete, that is another higher step, which is 276 kilometer meter. So that means first step, that is for steel, and second step, that is for the concrete. That means before concrete fails, steel will fail. And as I have told you yesterday, this is underenforced section. That means we shall allow steel to fail, because then we shall get certain warning. But if concrete fails first, then we shall not get warning, because it is a brittle material, it will fail. It will fail immediately without giving any warning. So this is the way we do the design. So this is the problem that we design this particular one here. So you have any other question here for understanding this particular one here, then you can make a comment so that I can come for your query, I can answer your query. So this is the one, that first problem. So this is the one for the longitudinal reinforcement. So that means here there is one issue. Deliberately I have shown this particular one here. You are providing here, the 6 bars. So you are providing 6 bars. How much I have to provide? Clear cover. This one here also I shall provide 25. So this one also 25. So 2 into 25, which will be equal to 50. Then I am having gap 1, 2, 3, 4, 5. So 5 into 25, 125, and I am having 1, 2, 3, 4, 5, 6 bars. 6 into 16, so 96. So how much I am getting here? 11. So I am getting here 271 millimeter. So please note that I have got 271 millimeter, but what is the width of the beam we have chosen? That is 250 millimeter. So shall I provide that one bar outside? Obviously not. So what is the alternative? How shall we solve this problem? Obviously one solution is that I can increase the width of the beam, maybe 300 millimeter, and that way we can do it. Alternatively, let us try another option. Let us see that option how it goes, because I can find out this one here, that 6 into 201 equal to 1206 millimeter square. And if I use, I can provide 420. If I provide 420, which will come here 4 into 314. So 1256, little more. Anyway, it's all right, little more. The 1256 square millimeter we are getting here. So in that case, what will happen then? Then I am getting, this is 2 into 25, no problem. This one will be, then my gap will be here, how much? The gap will be here 1, 2, 3, 4, 1, 2, 3. So 3 gaps, 3 into 25 and 4 into 20. So here I am getting 50, here I am getting 75, here I am getting 80. So 5, so 205 and less than 250. So if I take that one, say 16 millimeter, obviously I shall more number of bars, but that is coming close at the 1206, because I need not actually, then it is economical, no doubt, it is coming more 1256. So in that case I shall not be able to provide this one, because it is working more than width of the beam. But whereas if I follow the alternative one using 20 millimeter dia bar, we can provide, and which is coming less than 250 millimeter. That means within your beam you can provide. Now, what we do sometimes actually, whenever we go for your what is we call it, say at site, say for example, just to give you idea that at site, because the thing design office, they do that calculation, all those things, and on the basis of that they provide. Now at site, let us say if you do consider this one in series, then what problem you will face? If we consider in series, the problem you will face, that one, say first you will design it, then it will be, then it will go to site, then site will check how many bars you require, 16 millimeter die bar, 8 millimeter die bar, 12 millimeter die bar, 20 millimeter die bar, 25 millimeter, how many bars you require, they will calculate. On the basis of that they will give the order, and obviously that you will not get immediately on the next day. It may take 2 months or 3 months to get the get your materials. So that's why what they do at site, they find out based on that experience or from the design office how many ton of say 8 millimeter die bar they will procure, how many of say 12 millimeter die bar they will procure, how many 10 millimeter die bar they will procure, like that 16, 20, 25 that they will procure. Now at site, even if you are getting the drawing which is particular diameter, then they will do it that equivalent, that means 6 into 201 means 1206. So you can provide 420, though it is not in the drawing, but you can see it is safe because you are providing more. And obviously you will never provide less than this value. That means you should never give 320. You should always give the value which is coming more than this. This is the way also we do it at site. So, so now let us come back to the next problem, because this one we are talking say longitudinal. Now let us come back to the problem 2. A rectangular beam of size 300 millimeter into 500 millimeter is having tensile reinforcement of 3 numbers 20 dia. Design the beam to carry a design shear of 200 kilonewton using concrete grade of M20 and steel grade of Fe415. So this is your that objective that particular on here. We are taking another problem where we are having that. Okay, there is one question, very good question, that since I have given you an example, that where we are having that one, that condition where we are having 250 millimeter the width. The question is that shall we increase the diameter or shall we increase the width? That is very interesting thing. Now the thing is that here, um, if you, I shall prefer this particular case, I shall increase the diameter. Why? Because I don't want to do the calculation again. Because if you do the calculation again, because if you increase the width of the beam, then you have to do the whole calculation again, because you have to check that one whether what is the, how much is the concrete you are getting, that one say resistance, how much you are getting the steel resistance, all those things are coming here. But if I increase it just only diameter, so then there is no such problem here. So that's why I prefer this one, just only increasing the diameter at this case. But if you consider from the economic point of view, obviously the increasing the width, actually it is the concrete only will be, that concrete you will have that one, that your say quantity will be increased, but whereas steel quantity will remain same. So from economic condition, if you really consider, if you are compelled in that situation, then obviously it is better to go with the increasing the width. That is another part. Second one, that 250 millimeter, that is say thickness of the wall. Now let us say you are giving say some value, say 275 millimeter you are giving. So obviously the certain portion actually it will go out of your that wall. So that also it does not look good. So these are the different conditions you can find out. This one you can find out here, that it is better to go with the increase in the diameter of the bar. I am informed that there is certain kind of sometimes network problem, because of that it happens. Please confirm that whether now whether you are actually hearing me properly. So now next problem, let's come back to the next problem, that 300 into 500 meter, and that we would like to find out that shear. So again, as you can see this particular one here, so now characteristic strength of concrete FCK again 20 Newton per square millimeter. One thing just to inform you, these all those things actually I have this one actually all the that your example solved not manually, but I have done it through programming that I have done. And this particular problem, that all those things I have given 2.1, 2.2 like that, all those things I have given here. This one actually this one in that manner, and this particular one, that programming language I have used, that is Python. You can try on your own also, it is available freely. This is out of the context of this course I am talking, so you can use that particular one. So now characteristic strength of concrete again FCK 20 Newton per square millimeter, characteristic strength of reinforcing steel FOI 415 Newton per meter, design shear 200 kilonewton, width 300 millimeter, overall depth 500 millimeter, clear cover 25 millimeter, tensile reinforcement, that is provided 3 numbers of 20 millimeter, that is already we have told, because this one first we check the bending. So 3 numbers 20 millimeter there, that is already informed. That is, this is the actually first we check the in beam, first we check, we find out the depth of the beam using flexure, using bending or using bending moment, and then we go for shear check. And if shear reinforcement or stirrup required, that also we provide. So design shear VU 200 kilonewton, width B 300 millimeter, overall depth D 500 millimeter, clear cover 25 millimeter. So these are the information. It is very easy to give since I am doing by programming. So this is I have given. Tensile reinforcement 20 millimeter dia 3. So it is coming 942.5. So you can consider actually 942 square millimeter, that is sufficient, that because, and please remember that one, say always you should remember for 80 millimeter die bar 50.5, 10 millimeter die bar 78, then 12 millimeter die bar 113 square millimeter, 16 millimeter die bar 201 square millimeter, 20 millimeter die bar it is 314 square millimeter. That you should all remember this one, that when you solve problem, then you will find out that it is very easy to remember, and then you'll move very fast. Percentage of tensile reinforcement PT 100 AST by BD. So that value I have used it here, 300 into 465, and then you are getting here. That means 500 minus 25, 475 minus 20 by 2, 10. So which is coming effective depth 465 millimeter. Critical shear stress as per table 19 of IS 456 for this value, because this particular one, that is 0.68. So this value I am getting here 0.536 Newton per square millimeter. So just to give you, let us just go back to that value just to show you. So this is the one we have used, and from there we are finding this value. That means from there you can find out the corresponding value from there, and this is just linear interpolation that you can find out from this particular one here, just to give you idea that where from you are getting that value. Okay, so we are getting this 1.536 Newton per square millimeter. This value we are getting it here from that table. You have to find out that, so that we can use this value, and that one you will do it that by linear interpolation. So critical shear force, because that is the value of tau c, that is the value of tau c, this is called tau c. So tau c critical shear force VC equal to tau c BD, this one D is 300, this one, so 74.799 kilonewton. So this is the one, but how much is the shear force? The shear force is 200 kilonewton. That means here the only that you would say steel and you would say dowel action, aggregate interlock, concrete, that whatever we have discussed yesterday, which those all combined one, which you can get from table 19 by percentage of steel, and which is giving here say 74.799 kilonewton. That means it can go up to resist up to that. Now balance shear force there we are having 125.201. That means for this I have to provide the stirrup. I have to provide that one because this additional one, whatever you are having, that for that we have to provide stirrup or shear reinforcement. What is the area of shear reinforcement here? ASB. There are actually, yesterday I have told that two-legged, that means there are two vertical bars that whenever you are having, so there is two-legged we call it. If you require, sometimes you require three also, sometimes you require four also, that means four-legged, like that, depending on the situation. So if we consider this one here 101 millimeter square, number of legs here actually 2, shear reinforcement bar 8 millimeter, spacing of shear required 135, that particular one we are getting, and spacing of shear reinforcement provided, let us say 100. So this particular one we can consider here. So shear resistance due to stirrups 0.87 FY, ASB is 101, D by SVP 100, so 168.78 kilonewton. So that means we require here 125. I am not writing now, I am just showing in on the screen. I am just showing on the screen. So critical shear force VC, that tau C BD, that particular one we have got it. So on the basis of that, and then I am finding shear resistance due to stirrups 0.87 FY, ASB means two-legged, that's why it is 2 into 101, already we have calculated. D is the one, D is the one. So shear resistance due to stirrups VUSP 168.78. So how much here? So critical shear stress 74.799 plus this 168.78, which we are getting 243.579 kilonewton. That means we can find out that one 243.579 kilonewton that we are getting. So our applied shear, that is 200 kilonewton, which we have to resist, and for that we have calculated, that means if you provide 8 millimeter dia two-legged stirrup at 100 millimeter center to center spacing, you will get 168.78 kilonewton and shear resistance provided, so 243. That means our criteria is met, so the structure is safe. So this is the way we do it actually, step by step, that first we go for beam and then we solve the problem and then we can find out that. So this is your problem, we solve it. Now let us go third problem. A rectangular beam of size 300 millimeter into 400 millimeter carrying bending moment of 200 kilonewton meter. Yesterday at the end of the lecture we have discussed doubly reinforced section. So whenever we are doing, because the thing is that it may be from the architectural point of view, it may be from the client's point of view, or it may be from the practical point of view, that where you cannot provide the depth whatever you required, because so far whatever we have discussed, that is called singly reinforced section, the section where in the tensile side only you are providing reinforcement. In the compression side, in the concrete side, that you know, though we provide that one say bars, but please note those bars actually we are providing that hold the stirrups, that is not the one from the strength point of view. Now the question is here coming, that if you have that situation, a rectangular beam of size 300 millimeter into 400 millimeter carrying bending moment of 200 kilonewton meter, design the beam as a doubly reinforced section. Concrete grade here M25, steel grade Fe415. Please note that I am telling always, suddenly out of the blue I am taking M25 Fe415. Please note, for a particular project, whenever maybe a building, maybe it's a bridge, whatever is a structure, there should be certain kind of criteria in the very beginning itself, and that one actually decide in the very beginning whether which grade of steel, which grade of concrete you are going to use, what is the general say layout. So those things decided first. Later on you check that one, you analyze, you design all those things. So this one in the very beginning actually it is decided that whether you are going to use M25, M20, M30. For buildings generally we use say M20 minimum, then M25, we go M30 also. If we consider say bridges, there you will find out that we start with say something say M30 or M35. That is the one actually different cases we use that way. Now, tensile reinforcement provided by 20 millimeter dia and compressive reinforcement provided by 60 millimeter dia. Here also that I have given restriction. The tensile reinforcement I am providing 20 millimeter and compression one we are providing, that is at the top, that is actually 16 millimeter dia we are providing. So, again the standard way, characteristic strength of concrete 25 Newton per square meter, reinforcing steel 415 Newton per square meter, design moment 200 kilonewton meter, width B 300 millimeter, overall depth D 400 millimeter, clear cover 25 millimeter, moment of resistance due to concrete. So, concrete, how much it can take now? This is 0.138 FCKBD square, which is coming 137.672 kilonewton meter. So, concrete only can take this much, that means, but we have to resist how much? 200 kilonewton meter, that means we are quite short of 201, that means we are short of almost, you can say 62 kilonewton meter or 63 kilonewton meter, you can say that is short. That means that definitely the structure is going to fail if you only provide under reinforced section. And area of balance steel, that means this is the one for concrete, that this much of moment it can take concrete, and this is the balanced tensile steel which is coming 1307, let us say 1308 square millimeter. So, we are getting 1307 or 1308 square millimeter, that we are getting 0.36 FCK by 0.7. From there we can find out the value, and we have getted, because I have given the whole formula how we are using. So, you can check that one where from I have got it. So, AST equal to this much, this is from the equation of C equal to T, that means compression equal to tension. From there I can find out, that means here 0.87 Fy into AST will be equal to this much. So, this is the one from their formula I use. So, this is 1307 square millimeter. So, that means if I can go up to this, I cannot go beyond that. That means the section which I have given you are here 300 millimeter by 400 millimeter, as per the theory of reinforced concrete structures, concrete, I can go up to 137.672 kilonewton meter, that is the moment, and area of corresponding area of steel can be 1307. So, I am short of 63 kilonewton meter, that which I have to still I have to resist, and who will resist that? It will be resisted by the additional steel. So, additional steel will resist that one. So, if I only increase the tensile steel, that means if I provide say 1307 plus say something X, it will not help me, because concrete is steel weak. So, I have to strengthen concrete also. So, I have to strengthen concrete with the compression steel. So, this is the one I have to, because this one is in equilibrium position, that C equal to T. So, if I add something on the tension side, that means I am increasing certain force, then other side if I do not neutralize it, then obviously it will move and it will fall. So, that is why in the tensile side I have to provide the reinforcement, and equivalent reinforcement I have to provide in the compression side. Why I am telling equivalent? Because in the tensile style side, whatever you are having your stress in the tensile side, the compressive side the stress will be different, because if you consider Fe415, here the strain is 0.0038. So, 0.0038, that is the strain, but in compression side, that means in the concrete side, it is maximum 0.0035. So, that means obviously I am not getting that up to 0.003, that means steel will never be, compression side steel will never be able to go up to the maximum stress possible. It will be always less than certain value. So, coming to this one here, just to give you idea. So, let us come to this particular one here. So, we are providing this one here. How much we have given? The 300 that I have given. Then I have given 400. So, first thing, and we are providing steel here. So this is your that thing. See, so this one can balance that moment mu 137.672 kilonewton meter. But I have to resist mu 200 kilonewton meter. But I am here, that means this particular section, whatever we are having, this is called singly reinforced section, which can resist up to 137.672. So I am getting it here, and the corresponding area of steel, we call it say AST1, which will be equal to 1307.9. I should not be so so much actually that accurate. Here we can say 1307 or 1308 could be sufficient. You can use actually area of steel in 1308, no need of going for decimal, that you can try. So coming to this one, reinforcement to be provided in excess of balance moment, which we are getting it here, mu minus MUC is coming 62.6328 kilonewton meter. Now I have to provide reinforcement for steel, which will be in the compression side as well as for the tensile compression side as well as the tensile side. So I have to provide reinforcement here also. Sorry, some reinforcement I shall provide here, some reinforcement along this line I have to provide reinforcement here. This one is giving me say ASC, this one I have providing AST2. One we call it say AST2, another one we call it say ASC. So this particular one, if we consider here, then how much will be the steel, that I have to find out. Sorry. So I have to find out that ASC, and then I have to find out that. So what we are doing basically here, this one I am doing it here, that whatever steel I am providing here, let us say C2, let us say this is T2, C2 will be equal to FSC into ASC, but T2 will be equal to 0.87 FOI AST2. So C2 will be equal to, because this C2 and T2 should be equal, because this one now in equilibrium position. That means here C and T are equal. Here also just simply in one side I cannot increase. If I increase it, then it will be unbalanced. So I have to provide in both sides. So here the problem here you have that this one I am providing at the same level, because I am having the strain of 0.0038. Please note, we are having the strain of 0.0038. So I can use the same formula, that 0.87 FYS2, but here we have a difficulty. What is the difficulty? The difficulty here, this is 0.0035 concrete, so 0.0035, and I am providing reinforcement little below, which is D dash, effective clear cover. Effective clear cover D dash means equal to CC plus phi by 2. In this case, phi equal to 16. So I am considering this particular one here D dash. So that's why I am providing here and here, and this is how much? This one equal to D minus D dash. Please note, this one lever arm, that is different, and here lever arm is different, because we are considering this one, this is at the D minus D dash. So I am getting that. So here I am doing one here. Additional tensile reinforcement required AST2R equal to mu2 divided by 0.87 FY D minus D dash. So 62.328 into by 6 divided by 0.87 into 415 into 36 minus 33, because D dash I am considering here. So I am getting here 520 square millimeter. Strain in compress, because 33 means 25 plus 8 by 2, because in the compression side I have considered the 16 millimeter diameter. So 33. So which we are getting here 520 square millimeter. Strain in compression. Now the thing is that here, as I have shown you here, that I have to find out, because 0.0035, the strain obviously will be less than 0.0035. So add this distance how much, and that is the value I have got it here. So 0.0029. So 0.0035 into this particular one I can find out. From there I can find out the value of the one, that is 0.0029. So stress in compression steel, from the same curve you can do it, or in few books they have given one table also, which I have circulated also. There also you will find out that your stress strain, that curve also, the stress strain values are given actually there. So you can find out that once stress in compression steel FSC, which is 353 Newton per square meter, which is less than 0.87 FY. So compressive reinforcement required mu2, this value, divided by FSC d minus d dash, which is equal to 62.328 into 10 over 6, this much, which is coming 531.9 square meter. That means you see this one 520 square millimeter, and this one I am getting 531 square millimeter. That means this is more than that. That's why I was telling in the very beginning of this particular problem, that when we are discussing that we require compression steel more than the tensile steel, and this is because that your strains are not equal at two levels. Where you are providing the compression steel, there the strain, that value is less than the strain at the tensile level. That means in this case it is 0.0038 for the tensile one, and we have calculated that is 0.0029 at the compressive level, and obviously it will be less than 0.0035. That's why this area is different. So how much will be the steel then? This one will be equal to 520 plus 13.8 say. So 520 plus 13.8 means, so will be 1828 square millimeter. So you require tensile steel of, so I am getting it here, say 1308 plus 520, 1308 plus 520, and this case I am getting say 532. So 13.8 plus 520, so which I am getting here 1828 square millimeter, and this one I am getting it here 532 square millimeter. So if I get 1820 square meter, I have stopped here that with this particular on 1828. So if I do that, so one way I can get 620. That means further you are getting here 1884, and this one 316. That means I am getting here 603 square millimeter. So 603 square millimeter you are finding here 1884. On the basis of that you can calculate that how much is the strength. That means you will find out. So here this is the one that we do it. That means we have to, please note this one once more. I am trying to tell you that in your stability and force section, first you have to calculate how much, just to recapitulate this one. First you have to calculate the bending moment for the balance section, how much that it can take, and what is the corresponding steel, that you have to find out. That additional bending moment to be negotiated by adding tensile reinforcement and adding compressive reinforcement. Since the strains are different at two levels, where in the tensile case the strain it is for Fe 415.0038, and which will give you the corresponding stress of 0.87 FOI, but whereas in the compressive side it will be little below the top face of the concrete, that is where we are having 0.0035. So below that it is here it is having 0.0029 in this case. So stress you will not be able to achieve the full strength of the steel, which will be less than 0.87 FOI. And in that case, you will find out the value. So in that case, you will find out the value of that stress, and you can find out the corresponding area of steel. And obviously, the area of steel, if you compare both of them, say 531.9, which is coming more, little more, obviously more than this value that you are getting, then only you can say it is now in equilibrium position. So this is the idea of the doubly reinforced section. There is a question: what is the minimum size of bar we can assume for reinforcement in both zones? Okay. First of all, why I have chosen this one, say 20 millimeter and 16 millimeter. I could choose 20 millimeter also, or I could choose, say, your 16 millimeter or 12 millimeter also. Now let us say we have got it here, the value we are getting here 532. If I am getting 532, the objective is that first of all, at the top, that means in the compression side, we just provide hanging bars. So there generally you will find out that reinforcement diameter reinforcement little less, maybe 12 millimeter, even if you consider that, whereas in the other side you are having 20 millimeter, 16 millimeter, like that. That's why we have chosen in that particular one. Now since you are having, say, 532, if we are having 502, I can use here 220 bar also. If I use 220 bar, then it will be 2 into 314. Say for each 20 millimeter dia bar, each 20 millimeter dia bar cross sectional area is 314 square millimeter. Please try to remember these values, then it will be really useful for you and for your rest of your life. So if you solve few problems, and then immediately you will be able to remember these values. So for 16 millimeter dia bar 201, 20 millimeter dia bar it is 314. I can use 314 into 2 means 628. So 614 square millimeter into 2, which is coming as 628. Whereas in 316 I have provided, that is only 603, which is very close to the actual value. So this is the one you can do it. This is the one you can do. This way you can find out the value. So you can find out these values this way. I hope that it is clear, because the life could be very simple if you provide the same diameter bar. But as you all know, life is not so simple. Life is very much complex. So your economy, safety, so many other things are there. So in this case also, it is better to go ahead with, say, 16, or even if it is possible 12 millimeter dia bar also you can use it. So if it is, say, 113, so 113 means 5 12 millimeter dia bar, it will give me 565 square millimeter, which is much closer to 532 square millimeter. So this way you can find out. So there is no such actually it all depends actually to the designer, how much bold he is or how much he is adventurous. Sometimes there you will find out that designers, it depends on person to person also, and you can find out that designer, he is very much conservative, because the thing is, whatever reinforcement required, he is giving little more than that. So the issue is that whether you will believe your calculation or not. Obviously I do believe my calculation, and on the basis of that, whatever value I am getting, so in this case itself I can use this 12 millimeter dia bar, and I shall pay for 5 numbers of 12 millimeter dia bar, because cross sectional area of each 12 millimeter dia bar is 113 square millimeter. So 113 square millimeter into 5, which comes as 565 square millimeter. So if it comes 565 square millimeter, which is very close to the 532. So this way we do it. So that means you will find out the designer who is actually very much not only he is very much concerned actually with the economy also. Obviously he is very no doubt he is concerned with the safety, but at the same time he is equally concerned with the economy also. And in that case he may pay for 5 12 number bars in this case, so that he will come very close to that. Because if it is a small building, there is no problem, you will not get much difference. But whenever you are going for say real estate, there are so many buildings they are making, say for so many flats, so many things they are making, and here if you could achieve little bit, then obviously that you will achieve more. Say for example, just out of the context, just to inform you, say for example your road, highways, there you see that it is kilometers after kilometers, and you imagine that if you can save 1 millimeter thickness of the highway, then how much you can actually save. It looks like 1 millimeter for a small stretch, it is nothing, but kilometers are kilometer for the whole India. You just imagine that 1 millimeter, that how much actually you can save. So that is the way actually that it all depends on the designer, and design, obviously designer to designer it depends. Because I have seen many more actually that some few of them are very bold. They are they always prefer to go as per the calculation as close as possible. Few of them they do not care, okay, whatever it is that they can do it, they can use it. Say for example 316 or even say 220 also, that they can use it, because they. But another one important part also I can say, so far the design concerned, because now let us say that you are going for procurement of that one. You are procuring say 20 millimeter die bar, you are procuring 16 millimeter die bar. So now the small amount of the 20 millimeter die quantity, it may be difficult to get, and even if you get, finally you will not be able to use it properly or other way. So there are certain things also at site also, it depends that from the easy construction. Say for example you are having so many types of bar, so many, because if you go for actually your design, if you go for design, then economic, then different places, different sections are there. But for that actually it will be another problem at site. It will be very difficult to execute. That means one side you are trying to save something, but in the long run at site, because of that, to achieve that one, you have to do so much work and so much labor, so much thing, all those things you have to do it. And because of that, what will happen actually, you will not be able to, finally you will not be able to gain what you were thought of. So there are so many other criterias that you can find out, that it's not a simple one that we can go ahead with that, or how much quantity is required, how much time it will take, how much time it will take, that is there any difficulty in execution. So those things are also equally important. At the same time, I also prefer this way, that at site you can imagine that, because it is no doubt it is unfortunate, but anyway, say for example that our laborers are not so literate in that way, and then what happens actually, there is a possibility of mistakes, and there are many more such cases are there in structures, that it has failed because of say wrong placement, other things, it happens. So if you have say many more actually your that different kinds of say reinforcement at different places, so you have to check every time, you have to check your drawing, and which is not at all actually, this is not proper, because drawings you are using at site, you just use few times, you will find out that drawings have become dirty, that it is torn, and it is very difficult to use. So that's why there are many more other things. It is not the only one simple case you can use that way, because the design practitioner, they consider many more such cases. But anyway, considering that size, actually you can say that as so what is the minimum size of bar we can assume for reinforcement in both zones. I hope that you are telling in compression tension, that particular one here. So obviously you can consider that number one, width of the beam, that is first of all, that you cannot use, say for example I shall use say 10 millimeter die bar. Generally in lintel you will find out 10 millimeter die bar, but if you use that so many number of bars, you will find out you will not be able to provide that within the limited width, because whatever the reinforcement required, that also you have to find out, and you have to criteria that what is the gap between the two bars. So how much gap you have to give? You have to give the gap between two bars. One is that 25 millimeter, the diameter of the bar, maximum diameter of the bar you are providing. You are providing say 16 millimeter dia, 12 millimeter dia bar you are providing. So out of that you have to take 16 millimeter, and then you are having another option of 20 millimeter. So 16 and 20 out of the 25, out of that you have to use 25. So this is the one, that gap you have to provide. Let us say you are using say 32 millimeter dia bar you are using. So when you are using 32 millimeter dia bar, then 25 millimeter will not be, you will not be the governing one. In that case, the gap between two bars you have to provide 32 millimeter. So this is the way that we consider, that we find out. So it's not the one, but generally we provide 12 millimeter minimum, that bar we provide. But you have to accommodate those bars within that space given to you, within the width of the beam. I hope now I am clear to you, I hope. Okay. So next one, let us come back to the another problem. Let us come back here. Design a rectangular slab of size 4 meter. Design a rectangular slab of size 4 meter into 5 meter of interior panel. Design load is 10 kN per square meter. I have directly taken 10 kN per square meter. We shall do tomorrow that multi-story frame, we shall discuss. We shall go ahead, then you will understand that how much load, other things, how it is coming, all those things you can find out. So design a rectangular slab of size 4 meter into 5 meter of interior panel. So once more, please allow me to go to that IS 456 so that it will be clear to you what I mean. So I am going to the slab. So slabs in two direction. There is one-way slab and another one is called two-way slab, that particular one there. And it all depends that if it is obviously that we are talking slabs mainly rectangular, and one side we are having LX, another side we are having LY. And we always consider LX we consider as a shorter one and LY we consider as a longer one. So on the basis of that we find out the we calculate that on the basis of LY and LX. So coming to this one here, I am not going to detail of all those things because we are having middle strip, then edge strip, there are so many other things are there. We provide reinforcement, but mainly we are considering the main reinforcement. Our main objective that we are coming to the main reinforcement, because later on you will find out that other reinforcement, how much you are getting, how much to provide, that you will find out from this particular clause, that from this annexure, Annex D, the slab spanning in two directions. So all the information you can get it here, but we are mainly concerned with the for the timing here, that with the main reinforcement we are interested. So this is the one, actually I hope you are familiar with this one, this particular one, table 26, and we have actually total 9 cases, 1 2 3 4 5 6, like that we are having 9 cases. What does it mean? Let me just, before coming to that problem, just let me give you that. So if we have, so this is the one, that is, these are called panel. So if we have panel, then obviously this is one such thing. This is actually called interior panel, because all sides we are having slabs. Now the next one is that one short edge is discontinuous. Let us consider this one says short. That means this one we are talking that one short edge discontinuous. That means this is panel. This panel, one short edge continuous. In this case, one short edge continuous, and that's one. So this is the one short edge continuous. This one. This is longer side, and this is shorter side. So we are having this one, you say shorter side. So we are having this particular one here, shorter side you are having that, and then one long edge, if we consider this one say long edge, like that, one of them I can consider this one as a long edge. Long edge discontinuous, this is the one we are talking. This is another panel. So for different cases, we shall get different value. Two adjacent edges discontinuous. These are called adjacent edge. This is actually your adjacent edge. This is also adjacent edge. Then two short edges discontinuous. So two short edges discontinuous, that is this particular one I can consider. So I can consider in one side I can say two shortages. If the panel looks like that, this is one shortage, this is another shortage, that one discontinuous. This particular case I can consider. Then two long edges discontinuous. That is also possible, like that we can make it. Two long edges discontinuous. So like that, if it happens like that, then we are the case. Three edges discontinuous. That is also possible. That where we are having some kind of things like this. Three edges discontinuous on panel, you are having three edges discontinuous and four edges discontinuous. That means it is isolated. It is isolated like that. All edges are discontinuous. So we have such a 9 such cases we have, and on the basis of that, those 9 such cases, we can find out the value of alpha x and alpha y. So this is the one we consider, that one say alpha x and alpha y. That value we calculate. So we calculate the value actually alpha x and alpha y. That means if we have a panel, so I can find out the bending moment, bending moment, bending moment, bending moment. Similarly, I can find out that this way. That means I can find out the bending moment here, this and this equal, this equal say, and this one I can find out. So this is the value we calculate here. And we find out that one here, say I can consider say mu x, say alpha x w L square x, mu y alpha y w again L square x. Please note this one, w L square x for both cases is not w L square y. So this is the one mu x mu y. That means one side it will be mu x, this side say another side mu y, and then I shall find out at support and span. So I shall find out at support and I shall find out at span. So I shall get the value at support and then I shall get the value at span also. So for different value of Ly by Lx from table 26, 1, 1.1, 1.2, 1.3 to 2, we get the value, and on the basis of that we linearly interpolate. That means for different value of Lx, okay, we shall discuss that one at the end regarding width. When we shall summarize, that time we shall discuss. There is one question that could you explain it once again. We shall discuss that one. If it is this particular one, let me put it like that. That we are having nine different conditions we can have. Okay, I hope that you are asking this question. So whenever you are having this one, that panel, any floor, you consider any floor, and you will find out that floor actually divided by columns and your beams. If you see from the bottom, or if you see from the bottom to the top, look upward direction in the ceiling, you will find out that your say beams are there. That way you can consider. And if we have that one, let us say this is the plan. You are having columns here, beams, other things are there, So if we have this one, the plan, so this is the case we are having. First one, it is, that means say all the panels, please note this one I am talking plan, that means you are looking from the top, this is plan. Whenever you are looking this one here, so all the panels are not same. The panel here and panel this one will not be same. So that's why what are the different cases are possible, it is dependent on the your how the sides are connected. So first one, we are having interior panel, this is the one I am talking, interior panel, where you are having all sides are continuous, this side, this side, this side, this side, all of them are continuous, and that is the one as per table 26 I have to follow these coefficients. So I have the coefficients, so I have the value mu(x), which will be equal to say alpha x WL square x, mu(y) alpha y WL square x. So this is the one. So now the thing is, this mu(x) can be at support and can be at span also. Span means I am talking this one. So it can be here also, and it that means mu(x) can be here or here. Similarly, mu(y) also can be at support and also can be at span. That means it can be here, here, here. Now I have this is interior panel. Next one we are having that mu(x) and mu(y). So I have to find out that alpha x, alpha y. So that means I shall get one alpha x, I shall get it for support and for span. Similarly, I shall get alpha y for support and span. Now for different value of Ly by Lx, that means for a particular span, say Lx equal to 4 meter, Ly equal to 5 meter. So Ly by Lx equal to 5 by 4 equal to 1.25. That means I have to find out from 1.2 to 1.3, in between I have to get the value. So if it is interior panel, then I shall use this one. So for alpha y I shall interpolate, but for alpha x I shall interpolate. For alpha y I shall get the value that is a constant value for support and for span. Similarly, one short edge continuous, one long edge discontinuous, two adjacent edges discontinuous, two short edges discontinuous, two long edges discontinuous, three edges discontinuous, one long edge continuous, three edges discontinuous, one short edge continuous, and finally 4 edges discontinuous. These are the possible 9 cases that one can have, and on the basis of that we can calculate that you say mu(x) and mu(y). That means if you can now calculate mu(x) and mu(y), then again you can go back to the same your design principle. So now let us come back to the problem. Okay. So here design a rectangular slab of size 4 meter into 5 meter of interior panel. The design load is 10 kN per square meter. Again I am taking 10 kN. Use concrete grade M20 and steel grade of Fe415. So boundary condition of panel support, that is interior panel. Characteristic strength 20 Newton per square millimeter. Strength this one 415 Newton per square meter. Design load 10 kN per square meter. Length along x direction Lx 4 meter. Length along y direction Ly 5 meter. Length ratio Ly by Lx 1.25. Coefficient from table 26 IS 456, alpha x support 0.45, coefficient for that one alpha x span 0.034, from there I've calculated coefficient from table, that same alpha y support 0.0320, and then alpha span 0.024. So that means immediately after getting LY LX, I can calculate these values here, alpha x support span, that all those things we can calculate here. So design moment, immediately I can calculate MUX at support, alpha x support times WU LX square, so 0.05 factor 1, so 7.2 kilonewton meter. Design moment WX span, again I can find out that for that one, say 5.44, that means this is your MUX at support and span. Design moment MUY support 5.12 kilonewton meter, and then span 3.84 kilonewton meter. So I am getting these values, so immediately, so that means first I am getting LYLX, and then which particular panel, on the basis of that I can find out, with that I can find out the value, and then alpha x support span, alpha y support and span, and immediately I can find out the design moment, or how much we are getting it here, that we can find out here. So out of this 7.2, 5.4, 5.12, 3.84, the maximum is 7.2. So I shall find the depth of the slab on the 7.2 kilometer meter with B 1000 millimeter. Always we take for slab, we always take with 1000 millimeter or 1 meter, because per meter length we consider this one as per meter length, that we consider. So coming to the next, effective depth required mu by QB into FCK. So 7.2 into inverse 6, 0.138 FCK B, which is coming 51.1 millimeter, very less, 51.1 millimeter. Overall depth required dr means 51.1 plus clear cover plus diameter, so which is coming say 75 millimeter only. Overall depth provided, so I have provided actually that one, say 125 millimeter, I have provided that particular one, because we have not checked that one from the deflection criteria, sometimes we do it, but minimum generally we provide nowadays 125 millimeter. Earlier we used to provide 100 millimeter also, you can provide. For design purpose you could consider this one as 100 millimeter also, but anyway, this is your say 125 millimeter we are providing, that overall depth. Now here please see this one, this is very interesting to see. We are having reinforcement in two directions, one along X, let us say this way, another reinforcement like this. Now obviously the effective depth are not equal for both of them, for both direction. So clear cover, if I take 20 millimeter, effective depth for X direction dx, so d minus cc minus phi t by 2, which is coming 101. The other direction, so this is the outer one, that on the slab you will first see this one first. Over above of that you will get another diameter of that, which is the perpendicular of that one. That means these two bars are perpendicular, one along X direction, another one. So if we consider that, we are having this one say phi t minus phi t by 2, that another 8 millimeter I have to subtract, then only I shall get. That means please note, for MUX and MUY you are not having the same effective depth. For MUX you are getting more, whereas in MUY you will get one diameter of the bar less. So in this case you are getting 101 millimeter, and then you are getting another one 93 millimeter you are getting it here. So what I shall do now, I have calculated, or rather I have checked the depth of the slab based on the maximum bending moment out of those four. We have four bending moment in two different locations, one at support, another one span, and also in two different direction. So that is also in along X and along Y. So we are having four bending moment. Out of that we have chosen the maximum one. We have chosen the maximum one. So for 4.12 to 4.15 you can see that I have chosen the maximum one, that 7.2, because for that only I shall provide the depth of the slab. I cannot change the depth of the slab from one location to another location. I have to provide the same depth of the slab all through the room. we have to provide. So that means, and obviously I shall choose the maximum bending moment, and on the basis of that I shall calculate the effective depth of the slab, and then I shall provide, and in this case I have provided overall depth of 125 millimeter, and I have got two different effective depth, one along x, the direction is 101 millimeter, and the other one in normal direction, that is y direction, that one we are getting 93 millimeter. So this is the one we are getting here, but if I shall check the bending moment for all of them, I shall get it here. So lever arm factor jx, the x direction span, so I am getting it here 5.44, and I am getting 0.968, so I am getting 154.1. So I am providing here 8.200. I have provided all of them 8.200 center to center I have provided, which coming as 251 square millimeter. So this is the one we are getting 251 square millimeter you are getting here. Similarly, at the support, we are getting this value in the support, and then I am getting jx value similar fashion. I can find out area of tension required, that is I am getting 206 millimeter, and I have provided again 8.200 center to center, which is coming as 251 square millimeter. Similarly, lever arm factor jy span, I am only getting 117.4 square millimeter, and I am providing here 251 square millimeter. Lever arm factor jy support 0.965 and 158.1 square millimeter and 251 square millimeter that we are providing here. Now, there are certain things are there. In all cases, I have made my life very easy, easier, just providing 8 millimeter toward 200 center to center. And here in this case, the bending moment, your load is very less, 10 kilonewton per square meter. That's why it is coming. And most of the cases you will find out in the residential building, you will find out that 8 to 200 center to center is a very common practice. You will find out, because the load whatever actually comes on the floor in the residential building, there it is very less actually, that we can find out. Now this way we calculate that. Now the question is that one, how much is the minimum percentage of steel we shall provide? So that one we find out, again we go to the code and we find out there. So we calculate that. So whatever we do here, we calculate on the basis of this. This is the one that code available. So I can read it. The horizontal distance between parallel main reinforcement bars shall not be more than 3 times the effective depth of solid slab or 300 millimeter, whichever is less. So that means you can go maximum 300 millimeter or effective depth, that is your say 3 times the effective depth. Now here I have two effective depth, dx equal to 101 millimeter, dy equal to 93 millimeter. So I shall prefer 3 into 93, so 279 millimeter or 300 millimeter, whichever is less. So that means I can find out this one as 279 millimeter, because I shall not take 101 millimeter. Why? Because I have 93 millimeter in the other side, so I shall go ahead with the 93 millimeter. So 93 into 3, which is coming as 279 millimeter, or the code says or 300 millimeter, whichever is less. So this particular one we shall consider here. That means I shall not go beyond 279 millimeter. That means in other way I can say, to be more specific, I can go up to say 275 millimeter or 250 millimeter, that way we can say. So this is one generally we follow that occur on here, and these are available in clause 26.3 3.3, that particular one is available. You will find out that one here available here. Similarly, I can say another one. This is also equally important. That minimum reinforcement in beam, that is 0.85 by FY, and this is, please note, this is BD. B means width and D means effective depth, whereas maximum area of tensile reinforcement shall not exceed 0.04 BD. 0.04 means 4%. 4% BD means here D is capital. So that means the gross one. That means it is the one that overall depth. So whenever you are calculating maximum area of tensile reinforcement, that you are calculating based on the overall depth, not the effective depth. Whereas minimum reinforcement you are calculating based on the effective depth. So please note this one. This is very important actually. That particular one you should consider that. Similarly, there are certain things are there, just to give you idea, that your reinforcement, other things, all those things are there. So you can find out under these clauses, you can find out the longitudinal reinforcement in column minimum 0.8% of gross cross sectional area, 0.8%, or and maximum 6%. Maximum is 6%. Minimum diameter of bar in column, that is 12 millimeter. Spacing of longitudinal bars measured along the periphery of the column shall not exceed 300 millimeter. So like that, you are having all the calculations, all the things which is available in the code, and that you have to follow, so that it will be clear to all of you how much actually you will give. Okay. So coming to the next one with the what is called the problem, that whatever we have discussed, that one, let us complete the problem with that. So let us come to the end of that problem. So we have discussed this one, and then finally we are getting that different kinds of, for different cases we are getting that your reinforcement. So we have provided for all of them, we have provided. So all of them we have provided the reinforcement that we have found and that we have calculated. So this is the one I think. Let us so tomorrow we shall discuss on the, because whatever you have discussed, all those things we have discussed on the basis of that, say piecewise, as if the value is given out of the heaven. You have got the bending moment out of the heaven, you have got the width, all those things that you have got it, and you are doing the problem. But in actual practice that is not the case. You have to take the problem and you have to start from the beginning, and which I have already circulated. So we shall discuss that on tomorrow, that how we actually design a multi-storied frame. It is not possible to go ahead the each and every component, but major component I have already discussed, and also how to calculate that earthquake load. There are so many ways of calculating, at least minimum 2 ways, but we shall take the very common one. We shall take it, and that there is one problem here also today, but I could not finish it today. There is one more problem is there. So that problem we shall discuss, and tomorrow we shall come again at 10 o'clock for the last session of this particular course. So I hope that we are at the end of the class as per this one. The time now as per the is coming 12 o'clock. So have a good day. So thank you very much for listening, and tomorrow we shall again interact with the design of multi-story frame and all the detail. And then if you have any questions, other things, please go through that. I think that document is already available to you. Please go through that one, and if you have any question, that will be easier for me to explain also. So thank you.